Hi and welcome back for another video. In this video we are going to talk about a test to determine if an infinite series converges or diverges, and the test we're going to talk about here is called the integral test. So for an integral test, when we have an infinite series, let's talk about the conditions for which we can use this test. First of all, your terms have to be positive and decreasing. So you have to always check that these two things are the case. For almost every test that we do, we will be requiring positive terms for almost every test. But sometimes we also require that the terms be decreasing in value. It's not always the case, but for this integral test, you have to show that the terms are decreasing. The second thing we're going to do is we're going to take a look at our rule, and we're going to express it kind of as an equation. So for example, if we had a series where an was equal to, I don't know, 1 over n squared, what we would do is we would think of it as a function of x. And so the function of x would look like 1 over x squared. But for purposes of kind of keeping it, continuous here, we're going to just use the letter n instead of the letter x. So when you see f of n, I want you to think of it as being like f of x. So that's a function with the values of n. Now when we turn it into a function, what that means is n is no longer just limited to integral values. So you have all these, integer values. That's the word I'm looking for. So n is not limited to being an integer. It can now be any real number that's, between 0 and infinity, or whatever our value of n is for our series. So the other rule is that this function that we create has to be continuous, and it should also then be positive and decreasing. So if your series is positive and decreasing, your function should be positive and decreasing. You just need to make sure that it is in fact continuous on the interval. So something to look out for would be something like vertical asymptotes or things like that. So we'd want to be kind of mindful of that. Most of the time though, that's not going to be a huge issue, but it is something we do need to consider and make sure that our function is in fact continuous and that there's no holes or vertical asymptotes on that interval. So the best time to use this, well, if your function, if your rule an looks easy to integrate. So think like you would use, if you were going to do an integral, you'd do tabular integration, or maybe integration by parts, or a u sub, or something like that, or an easy antiderivative. Partial fractions likes to show up, so sometimes we have to do partial fractions with these with this integral test. So if it looks like an integral that you would use u sub, tabular integration by parts, or partial fractions on, that might be an indication that the integral test is what you want to use. So how does the test work? Well, the test works like this. If you can create an integral and you have this continuous function f of n, if the integral converges, well, then the series will converge. So it's as simple as that. So you'll need to make sure that as you're doing this test, you're going to express your integral as an improper integral with a limit, and you're going to show that it converges. You're then going to just state your conclusion. Because my integral converges, therefore the series will converge. But remember, you can only make your conclusion if you do those 3 essential steps. You need to state the conditions. In other words, you have positive decreasing terms of your series, and your function is a continuous function. Then you need to show the integral. You need to do the antiderivatives. That's probably something that they're going to be looking for on an FRQ to be able to give you a point for. You need to properly carry out that improper integral, expressing it as a limit as b approaches infinity and all that good stuff. And then you need to make your conclusion. So there is a lot involved in this test, and you need to make sure that you're checking all those boxes. So let's take a look. So use our integral test to determine if the series converges or diverges. So when I look at these two, I can easily tell, looking at both of these expressions, that if those n's or x's, I could find the antiderivative. So this one here on the left, 3 over x plus 1, the antiderivative is just going to be a natural log. The series on the right, if I express that as a function of x, the antiderivative, I'm going to use tabular integration to find it. So these kind of appear to be good integral test problems. So let's just take a look at our first one. So I'm going to state my conditions. The terms of 3 over n plus 1, or you can call it an, are positive and decreasing. And anytime you say something, you want to make sure that what you're saying is actually true. And here they are going to decrease. Anytime you have an n in the bottom of a fraction, as n gets bigger and bigger, that fraction will get smaller and smaller. Then what you're going to do is you're going to say f of n. So now we're turning it into a function, so n is no longer going to be just integer values. You're going to say that it's continuous. And it's going to be continuous on the interval 1 to infinity. And it's true, there is a vertical asymptote on this function, but it's not anywhere on our interval. It's at -1, so it's not in the interval, so we're good to go. But you're going to say it's continuous on that interval. And I'm getting those values from my sigma notation here, so from whatever n starts at to infinity. So now what we're going to do is we're going to evaluate the integral. And so I'm just going to say, okay, the integral from 1 to infinity of 3, and if you want to rewrite it as an x, if you're in the habit of just using x, that's fine. Nobody's going to care. And as a matter of fact, if you want to change your, n's in that first statement where we're stating our conditions or whatever, you can change them to x's. It really doesn't matter what variable you use. But it does matter that we express our integral as an improper integral. And then we're going to find our antiderivatives, and we're going to keep that improper integral. So this will be 3 ln of x plus 1. And we're going to go from 1 to b. And I can already tell that this integral is going to diverge because you'll have 3 ln of b plus 1 plus, or minus 3 ln of 2. And we're going to keep our limit notation, be really consistent so we don't get any linkage errors. But I can already tell, I know that this is going to be an infinite amount because as b goes to infinity, ln, the natural log of a bigger and bigger number, is also going to approach infinity. So this is going to be infinity minus this value, which is going to diverge to infinity. So what I've just shown is that this integral diverges. So now I'm ready to state my conclusion. So it's going to look a little bit like this. Because the integral diverges, the series diverges. And it's as simple as that. So let's take a look at the other one. Here, if I'm going to do an integral, I'm going to be using tabular integration. So it's going to look a little bit like this. I'm going to state my conditions. So this is the series, and I'm going to put the e on the bottom because that helps me see that this is actually going to 100%, the terms are going to decrease to 0. It passes, well, it doesn't fail the nth term test. If I use L'Hopital and I think about how that limit's going to play out. So these terms are positive and decreasing. Okay, now I'm going to rewrite it as a function, and we'll go ahead and just use x if we like to use x. So x over e to the x is continuous on that 1 to infinity interval. And then we're going to show the antiderivative, or we're going to show the integral. So from 1 to infinity, and I'm going to change it back to a negative exponent. We like those for integrals. I'm going to express my improper integral as a limit from 1 to b, x e to the negative x dx. And then I'm going to show my tabular integration. So I'm going to identify u. I always need to identify u and label u and dv, even if I'm doing tabular integration. So then I've got x, 1, and 0, and then I'll antiderivative e to the negative x divided by negative 1, e to the negative x divided by 1. So tabular integration plus minus. So now plug in my antiderivative. B is approaching infinity. So I'm going to have negative x over e to the x. I'm going to move that negative exponent down, minus 1 over e to the x from 1 to b. And so this limit, so as b approaches infinity, I'm just going to kind of mentally plug things in L'Hopital. I know that when I put b in, I'm going to have 0 minus 0. And then when I plug in 1, I'm going to have negative 1 over e to the 1 minus 1 over e to the 1. Clearly it doesn't diverge, so we're going to say that this converges. I don't need to work it out. I don't need to do any of that extra work of figuring out what does that equal. I just need to show that it doesn't go to infinity. So now I'm ready to state my conclusion. And I'm going to say since the integral converges, the series converges. And that's all there is to it. So here's my integral test, and it's as simple as using integration techniques to try and find the antiderivative and see if the integral converges. So let's try one last problem here, and this problem is going to involve partial fractions. And I know it's partial fractions because when I look at this problem, I can kind of see, like that it's factored on the bottom, and finding the antiderivative of this would involve partial fractions. Now, I will also give a little warning that as we learn more tests, there are sometimes more than one test that are appropriate in these situations. But since we're just learning this integral test, we're going to apply the integral test here. So first things first, the terms are positive. Okay, the terms will be let's see, hang on one. We're actually going to back up for 1 sec because as that problem was stated, the terms actually were not positive. So we're going to make one small minor adjustment here and just kind of make sure that we have a series that meets our criteria as we're learning. But if n was the original value, it was a 4, we would have some negative terms. So the terms would not all be positive. They'd be decreasing. Well, now we have terms that are positive and decreasing. So now, and actually, now that I look even a little bit closer, this does not meet the criteria for this integral test. So remember, our criteria are that the terms have to be positive and decreasing. So when I look at the terms of this, if I graph this function on a calculator, on the calculator, you have kind of this action going on here, and we have this side here, we see that our function is actually going to be increasing. So this would not be a very good candidate for the integral test. So let's pause for a moment, and we're going to get one that does work really well for our integral test with partial fractions. All right, so now we have another series here that appears to be a good one for integration, and this one is in fact positive and decreasing, and the function is continuous. So let's state our condition. So our terms are positive and decreasing, and if I write f of x as 7 minus x, x minus 1, x minus 3 is continuous. So now we're going to evaluate our integral. So we've got 7 minus x over x minus 1, x minus 3 dx. And I'm just going to, right off the bat, go ahead and express this as a limit as b approaches infinity, just so I can save a little bit of space. So now I'm ready to do my partial fractions. So let's remember that this involves taking a over one of the factors and b over the other factor, and setting that equal to 7 minus x over x minus 1, x minus 3. So we'll have a times x minus 3. So remember, this is all about getting that common denominator. So through that process, we end up with this statement in our numerator. And if we let x equal 3, then we get 2b equals 7 minus 3 is 4. So we get b equals 2. And then if we let x equal 1, then we get negative 2a equals 8. 7 minus, equals 6. So we get a equals -3. Partial fractions always take up a ton of room. So here we go. The limit as b approaches infinity. I'm going to make sure that I have a and b in the right spot. So a is going to be -3 and b is going to be 2. So when I go and rewrite this as my integral, I want to make sure I get everything in the right spot. And I want to put the -1 second. So I'm going to go ahead and put that b term first. So I'll have 2 over x minus 3 minus 3 over x minus 1. There's my integrand. Limit as b approaches infinity. And now we'll do our antiderivative. So we'll have 2 ln x minus 3 minus 3 ln x minus 1 from 4 to b. And remember, it is never okay to have infinity minus infinity. That's one of those indeterminate forms. So whenever we have natural logs in this scenario, we want to condense our natural log. And so I'm going to take and use the power property and turn the 3 and the 2 into powers. So this becomes the natural log of x minus 3 squared over x minus 1 cubed, and then subtraction turns our values into a quotient. So we'll have the natural log of a over b, if you remember how that works. And so this is that condensed form of my antiderivative. And notice whenever I square an absolute value, I don't need those absolute value bars anymore. If you leave them in there, it's not a big deal, but they're kind of redundant. We really don't need them. But now I'm ready to evaluate, and I already can tell that this series, or this integral, is going to converge. So as b goes to infinity, let's see, I will actually think about what as b goes to infinity, this value on the inside squared over this value cubed. The end behavior model is going to be x squared over x cubed, which is actually going to be 0. So I'm going to have 0 minus, and then whatever I get when I plug 4 in. So that's going to be a value, so 4 minus 3 squared over 4 minus 1 cubed. It's a positive value, so I don't need the absolute value. But essentially we can see that this definitely is going to converge. So now that I've shown that the integral converges, I'm going to zoom all the way back out so I can see all my work. And now I'm going to go up here, and somewhere in the mess, I'm going to write down that since the integral converges, the series converges. I think these are the worst ones to try to use the integral test for, because those partial fractions just take up so much space. But this is how this test is going to play out. So now you should be able to practice using that integral test on some of your series. You've got this.